my pleasure to introduce Dr. Carol Hayakawa. You gave your personal introduction on the first day, so I don't want to belabor the introduction, but Carol is formally trained as a mathematician, graduate and master's work at UC Berkeley and UCLA, with combinations of training in maths and statistics. She worked in industry for a long period of time, and very much looking at the uses of math for practical application, but then felt the urge to go back to graduate school.
I did.
And went to Claremont Graduate School at the time before it turned to Claremont Graduate University.
For the most part, was university. While I was there.
And to do graduate training in applied mathematics, and where she met Professor Jerry Spanier, and with that formed a very strong partnership. I met Carol when she about 1 or 2 years into her graduate school work, because Professor Spanier started an affiliation with Beck and Laser Institute. And so I got the privilege and opportunity to work with Professor Spanier and with Carol while she was finishing her PhD. I knew that I wanted her part of my group going back when, and I think we've worked for more than 20 years
25.
now. And she's just been terrific collaborator to work with, and really has really foundational knowledge in Monte Carlo, all applied within biomedical context. And so I think you're going to see kind of this very general introduction to Monte Carlo, which I think is useful, that Professor Zhao gave us, and kind of start to see, how it can be applied more directly to biomedical applications. So with that, let's welcome again Dr. Carol Hayakawa.
So my talk today will be on Monte Carlo, but now extensions and applications, a little further in from Professor Zhao's talk. So in this talk, I hope to review the traditional concepts that Professor Zhao comes at it at a slightly different angle, and I think it's always good to be taught a subject from different angles. It doesn't always talk to everyone how it's presented in one way. I'll describe perturbation and differential Monte Carlo. I'll describe how the frequency domain, and spatial frequency and temporal frequency domain estimators are derived. And then at the very end, I'll show you how to set up and execute a Monte Carlo simulation. So I'm going to show this little roadmap, and I'm going to use it again in the talk. So I wanted to, it's a review of Dr. Zhao's description, but I give a little more details. So we start with the integral differential equation, RTE, and we use a method of characteristics. This is a partial differential equation method, where you define these characteristic curves, parameterize the variables along constant curves. Characteristics allows you to simplify the equation, and then it becomes solvable in many times. In this case, it does. And we form an integral RTE. That was covered before. That, along with a detector function, allows us to evaluate a measurement. And one of the things that this collision density is a function that is defined in these functions called, and operators called S and K. So if we define the estimator in terms of the solution to the integral RTE, we ensure that it's going to solve the RTE. And just to keep in mind, the integral differential and the integral RTE equivalent forms, just different. So how do we do that? So we start, I've seen this time and time again. I think we're all using the same terms. So we have L is the radius. We have, I try to bold when it's a vector. So R is a position vector. Omega is a angular vector. We have mu s and mu a and mu t. Mu a plus mu s is mu t, total attenuation. P is the angular phase function. Q is the source. And the reason why we transform to the integral RT, like why would you do that if you already have the equation? Key things. You can show existence and uniqueness of the solution. big deal. And also you can represent the solution as a convergent infinite series. This is also a big deal. And this is something that Jerry Spanier did back in '69. So I'm not going to do the details. They're pretty straightforward. If you've taken a PDE class and done method of characteristics, Bell and Gladstone shows you really good details so that you can follow along. And you get an equation for psi, this integral form. Psi is the collision density, and it's related to the radiance by a factor of mu t. But you get this psi equals, and I call it fancy K. It's an operator. It gets an elevated font because it's an operator, and psi plus s, where the K, fancy K, is this operator, and in the integram we have, I give it a little plain K notation, and psi. This K in the integram has two components, C kernel and transport kernel. So yeah, so I call this transport. I think Dr. Zhao was calling it transmission, but in my terminology, I'm calling it the transport kernel. The C kernel takes you at a position R from a direction omega to another direction. And it is composed of the probability of scattering. So mu s over mu t is probability of scattering. Because mu a plus mu s equals mu t, mu a over mu t is probability of absorption. So if you do scatter, then P defines the angle that you're going to deflect in from the direction that you're in. And T takes you in a direction from position R prime to R. And it's given here, same as the equation you saw earlier. I just want to explain why there's an integral. So you have mu t as a function of the position you're coming from, an exponential to the minus. And in the integram, we have mu t as a function of this parameterized line because the mu t could vary along that track. If you have very heterogeneous tissue, then you want to make sure that you're moving with respect to the changes of the optical properties as you move along that line. Oops. And just to finish up before I go to the figure, so S represents the density of first collision. So it takes that Q source in the RTE and it transports it to the first collision. So to see how these are in action, we start with the source Q and we transport with S to its first collision, shown in the box. So that's its first collision. Now, it could also go over here. What I show in that little squiggly line is that that photon, when we invoked the collision estimator and asked, did it scatter or did it get absorbed? It got absorbed. That's a little symbol for I kind of make a shut up back sound. But it so but if it didn't, then it scatters, and then P is invoked to determine the change from omega prime to omega here, and then T comes in to tell you, okay, how long am I going from here to here? So yeah, that's kind of how the random walk rolls. If it, we run them until they exit phase space, which oftentimes if we're dealing with skin, it's just out the surface. And so, with the detector here, hopefully we catch some of the photons exiting. So as I said, one of the nice things about the integral form is that you can write it as a convergent infinite series. How do you get there? So I just took the equation before, I just rearranged terms here. So we have psi equals fancy K psi plus S. So I just brought all the terms, psi onto the left-hand side, and you get this form of the equation on the right-hand side. Now, if you've taken series and you look at the series 1 over 1 plus x, you can expand it in 1 plus x squared, infinite series. Similar thing, except for this is an operator. And the constraint on that infinite series converging is that the absolute value of x is less than 1. Here, the norm of this operator needs to be less than 1 for this to converge. And so we can expand this into its series, and then we have the s on the right-hand side. And what that means, this is called the Neumann series. A lot of people in rendering are familiar with it and use it in their talks too, so you might have heard of it. What it means is if we're interested in the solution psi at a position r at a direction omega, the solution is comprised of those photons that come directly from the source. So this could happen in a transmittance situation. Reflectance can't, because you have to scatter in a straight line right into that direction and position. Okay, so that's first term. Then it's the contribution of photons that scatter once and then contribute to that direction. So we're integrating over all positions and directions that will scatter into this direction that we're interested in. And then we capture those that scatter twice, and so on, until you get the final infinite series here that provides the total solution here. So now we have the solution everywhere in phase space, but we take measurements and we want to know what is being detected in a certain place in that phase space or on the boundary. So we're interested in a measurement. I've notated it as I, and the way that we evaluate that measurement is we take a weighted interval of the solution with a detector function, and that detector function is known. I give an example of reflectance. This is the detector function for reflectance. We have something called a chi function. Chi function is basically something that says, yes, 1, if you're in the spatial location, the spatial definition of the detector as well as the angular. You might have a fiber with an NA. So you might need to specify the delta angle here as part of your detector. And so this detector pretty much picks off those random walks that satisfy the constraints that you've defined in your detector. So now that we have, in a sense, an analytic formulation of the problem, we need a random variable. And we call that random variable C. It's a method of tallying. And the way that we define C is that we use the elements of the RTE, the S and K. K is that kernel that's composed of C and T, the collision and the transport. And we have a detector function. There's potential weights that get applied to the photon as it progresses along its random walk. And so the probabilistic representation of the measurement I is this evaluation of this random variable C with respect to a measure. Just think of a measure as something that arises from the probability density functions that compose S and K. So Dr. Zhao was describing how we have these functions that, take for instance, transport. It has a form of mu t e to the minus mu t variable x, and you can integrate that create a PDF, then create a cumulative PDF, a CDF from that. And the way you sample it is you sample a number from 0 to 1, come into that CDF, come down and see, okay, this is the distance I'm moving. Finally, once you have that estimator, the expectation with respect to that measure is evaluated by summing all the random variables over n, the number of photons launched. Not the number detected, but the number launched. So I'll show you the formulation of what C is for reflectance. We use this modified terminal estimator. It's called modified because there's a terminal estimator, and what we had to do for biomedical optics problems is that we have these photons making their way through the random walk. However, at this what happens at P3 is the transport, the T actually defines a distance beyond this. It happens to intersect the detector, but the T would actually put it out here. So what we do is we put a pseudo collision here because we want to detect right here. And also, you might also go through refractive index mismatch there, and have to go through Snell's, change angle, things like that. We put a pseudo collision there. So this is the random walk consists of these, and just to simplify notation, these P's represents the position and direction. So it goes from P1, P2, P3, and then there's this pseudo collision, which we kind of notated by the last collision to the superscript 1 to represent a typical random walk. So the modified terminal estimator looks kind of complicated, but you'll see that it gets simplified. In the numerator, we have the components of the actual integral RTE here. And in the denominator, we have the elements with respect to the measure, they're the elements that we're defining to represent, to move that photon, the density functions that we're using to move that photon through the tissue. And then we have the detector function, much like the detector function for the analytic representation. So earlier, we talked about analog random walks. So analog, the way that analog runs is that the photon weight starts with 1. It could get absorbed with the sound. If it doesn't get absorbed, then it continues on. Same with weight 1, weight 1, weight 1. And why this random walk is running this way is that we're actually defining the random walk exactly to be the definition that's found in the integral form of RTE. These A, S, and K's are exactly what's in the integral form. So all these, looks complicated. All these cancel to 1, becomes a binomial estimator that scores ping 1. If it hits it, 0 otherwise. You can imagine that if you have a photon very far from the source and a problem where you have lots of absorption, very few photons are going to make it there because they're going to get hit every time they collide with. Is there a problem with me getting absorbed? Yes. Yeah. Then you die. So instead, these methods, discrete absorption methods, have been designed to allow for certain problems, and it's not always to say that discrete absorption weighting or other, one is always better than the other. Depends on the system that you're modeling, and the optical properties you're dealing with, how far the source and detector are from each other. So in discrete absorption weighting, we still, so we still sample, the transport with respect to the mu t, e to the minus mu t. So when you do that and you form the expectation of that, the mean-free path between collisions is 1 over mu t. I think this might have been a length scale on the first talk. There might have been a 1 over us, which is the mean-free scattering path. So in discrete absorption weighting, you disallow the termination of photons. And instead, so we're changing the random walk, but you can't just change the random walk and hope that everything it turns out right. You have to adjust the photon weight appropriately. So this is not equal to just the numerator. We've got some denominator actions going on here. So when you fill in the estimator, we're going to get these factors at each collision. So at the first collision, we're going to get a factor of us over mu t about, so whatever it is at that collision and so on, because you could have a very heterogeneous tissue here. But if it were homogeneous, then you would get a us over mu t to the power k, k being the total number of collisions prior to detection. So that's discrete absorption weighting. So one of the things though is that because we disallow termination, this can roll, especially for semi-infinite media, this can run a long time. But basically, we'll run photons in, I'm gonna go over here, and then I'm gonna go out the surface, but nowhere close to the detector, but still, you're running it. And you could turn on something like Russian roulette to like it. We should add that to our simulation so we can hear it. Okay, so in continuous absorption weighting, so when we change the random walk, we're now transporting with respect to us e to the minus us is traveled in this continuous absorption weighting. So the mean-free path between collisions is now 1 over us. And we're changing the way that we're rolling the random walk process as well. And so when you plug it into this estimator, you're going to get these exponentials that take you from position to position, e to the minus, integrating a Loudon integral here in case you're always changing along that path. And at the end, if it's homogeneous, you get something that looks like Beer's law, which L is the sum of the total path. So the weight is getting continuously applied along the path length, whereas discrete only at the collision points is the weight, photon weight dropping. So I made a little video. So I took a situation where us prime over ua is 10. I give the actual optical properties. I made L star be about 1. So I'm going to give you a little measure here. So I'm going to show you, I'm going to stop this and show you, hopefully I can stop. Let's see. Okay. Oh wait, let me go one more. Okay. I think I went too far. I'll go here. Whoops. Okay, so here's where this analog photon got absorbed.
You're not Carol Matt.
You will never make me laugh. I can only smile at that sound. Although it is sad. Won't have that sound in DAW, won't have that sound in CAW. You'll see how the path of the photon moved along here. and with CAW here. Slightly different. I seeded them with the same C for the random number generators. Kind of has the same signature, but because this is sampling near collision distances using 1/US versus 1/MET, it's moving further on each collision. I'm also adding time in here too, because you'll see how analog has a benefit that way. So, okay, so after 1,000,000 photons, this is kind of what the absorbed energy for analog looks like. Discrete absorption waving and continuous absorption waving. You can't visually tell the difference here. Although if you look at the variance and the error, that really highlights when two things are dissimilar. Notice that this only took to run 1,000,000 photons took 6 seconds. Now, this took 93, this took 81. So yeah, one of the benefits of analog is it runs that many photons that fast. And then I added in a detector. And I just wanted to show you kind of photon bananas, if you will, of how, so what's happening in these bananas is it's the probability of a photon making it from the source to a voxel in the tissue and then making it out the detector. And I kind of move that detector. It gives you an idea of the sampling domain of the majority of the photons as they traverse. So everything shown in these bananas have necessarily detected. And I do it again for now higher absorption. US prime over UA. These are the times that you need Monte Carlo. Diffuse centrifusion's not gonna work for you. So I'll just let this one roll. But if you saw the maybe I'll run right until here. Oops. So you can see that way more, I think, if you were to compare the two, way more of spots are shown with the same number because they're getting absorbed more. Oh, I guess I have to run it until the end until I change my page, which is weird. Okay. So, okay, yeah. So going to change here slightly. Did you have any questions up till now? Okay, keep going. So I wanted to cover perturbation Monte Carlo. Perturbation Monte Carlo is a method to determine the change to a measurement due to changes in optical properties within the tissue. And one way, if you didn't have perturbation Monte Carlo and you wanted to see the difference between the measurement at this detector with solely the light pink tissue compared to the measurement at the detector with the light pink and the dark pink, then one way is you could run a simulation with just the light pink, and then you could run another at the dark pink, run another simulation. What you do in that, when you have a heterogeneous tissue, is that when you transport, you go to the pseudo-collision here, you figure out what's remaining on that track. I figured out the track using the optical properties at this point. I might have moved to this point, but I'm going to put a pseudo-collision. What's next? What's the remaining portion of that track? And what is it in terms of the new optical property? So it may be shortened, elongated, depending on how this delta A, and A I'm using as a vector to represent the optical properties, and these perturbed optical properties are alpha plus a delta alpha. So one of the disadvantages of running two separate simulations to capture the change due to the effect of this tumor setting or this heterogeneous region is that time, you have to run a simulation. Secondly, the way perturbation Monte Carlo runs is that we evaluate the change to the signal using the background set of random walks and reweighting them appropriately. So that evaluation can be done very fast compared to running an independent simulation. So how do we do this? So we take, and I'm just showing a homogeneous, it doesn't have to be, it can be heterogeneous and you can perturb on top of that. But just to keep things simple, I'm showing a homogeneous. We run the random walks. We keep track of certain pertinent information happening within this region of interest. We put it into a database. And this can apply to any kind of reflectance, spatially resolved, spatial frequency, temporally resolved, temporal frequency, fluence or radiance. So how do we determine I hat? What's the change to this signal, this measurement? Because we have this new region in here with the change of optical properties. The way we rewrite the photon is something called, we apply a radon-Nikodym derivative. We define the perturbed estimator as the baseline estimator, and application of this radon-Nikodym derivative. This mu hat over d mu is a radon-Nikodym derivative, where mu hat is the perturbed measure, or it's think of it as the probability density functions that arise from the changed optical properties. And in the denominator, we have the original random walks that will run in the light pink. So you can see that this perturbed measurement could have been performed by running a two-region or multi-region, but instead what we do is we use an estimator, apply the factor, and we can use the original measure to evaluate. So let's take a particular case and use discrete absorption weighting. The weight of a photon using discrete absorption weighting is, for the homogeneous tissue, is A, US over mu t power k, k being the number of collisions right before it exited. And A accounts for velocity to specular reflection. And what we do is we save information of all the random walks that ran. This random walk didn't go through that region of interest, so it doesn't put any pertinent information in here, or its pertinent information is 0. And then the ones that do, we save it in a database. And what we do, so for instance, say the change to alpha is the change to mu A and mu S in this area. We have a mu A and mu S hat. And so here's the background baseline weight. And here is that radon-Nikodym derivative. So here we have a C correction. C is that C kernel, except for we're using the C kernel for the perturbed optical properties divided by the baseline optical properties, put to the power j, j being the number of collisions in this region. If we were to have perturbed G here, we would have had the phase function correction in this factor as well. Here we have the transport, and basically if you kind of this, put you have in the numerator, you have a mu t hat e to the minus mu t L, and for each collision you do this in this region such that and put it over the baseline in the denominator, you get something that looks like this, where S is the total path length. Each collision sums up and then you get the path. So one of the things I show a plot here of reflectance versus source effective separation. I have the baseline, which is solid red. I changed mu A by a factor of 2 and halved mu A. So those two plots are shown next to it. And see how the little bumps are fault tracking each other. And that's working to our advantage. I'll explain why in a sec. Oh, yes. It evolves as you run the simulation. So as the random walk is rolling. As the random walk, as the random walk is running. So for instance, this random walk is going to have 1, 2, 3, 4 as its K. This random walk is going to have 1, 2, 3, 4, 5, 6, 7 as its K. And it only, so, you know, the detector functions involved here. So only those photons that are going out the detector this K is only important for those values because they're going out the detector. So yeah, it's photon based or dependent, and how it went through the random walk. Some photons, you know, because I'm just using some sort of, you know, image maker here, you know, it's very interesting. When you saw it, I mean, those random walks in the movies were actual random walks, depending on the optical walk. Really, they sometimes take very torturous, routes before they actually like go deep, and then they come back out, and their case can be quite large. Yeah.
When you say random walk.
Yeah. So the random walks, I should probably define that. So the random walk is the photon's migration or trajectory from source through the tissue. Some of those random walks will come out in the detector, some won't. Some might get absorbed. Yeah, so that's the random walk. Yeah, sorry. Good that you caught me on that. So now that we have PMC, an extension means that we can get differential Monte Carlo. Okay, so this is great because then we can get sensitivity coefficients. We can apply more robust gradient-based optimization methods for solving inverse problems. And how you form that is that if you take the derivative of the estimator and evaluate it with respect to the measure, it's the same as the derivative of the estimator. So I don't write out the terms, but basically you would take, this is the estimator, and you would take the derivative of that with respect to mu A or mu S, straightforward, bring down the J minus 1, very straightforward. And now you have an estimate for the derivative of whatever reflectance or whatever measurement you're taking with respect to now the optical. So you can see how that measurement is changing or sensitive to changes in those optical properties. So here's a plot of differential Monte Carlo. You can see again, it's got, it's kind of tracking. And why that's a good thing? Okay, so the good thing is that we're running the perturbed results based on a single set of random walks based on the baseline. So there's correlation happening there, and that correlation is actually working to our benefit because it's going to produce smaller error than if you were to run an independent simulation with the perturbed optical properties. Another thing is that you can, get the results for multiple perturbed values by post-processing that database, and quite a bit faster. Running an independent simulation takes 5 minutes. We can get the results in less than a second. And I show on Saturday how we can use Monte Carlo and these derivative perturbation and differential Monte Carlo to solve inverse problems. A long time ago, Monte Carlo could not be used to solve inverse problems because usually when you're solving inverse problems, there's some sort of iterative method where you have to use the model to, you take you move along and try to find the solution, and you have to reevaluate the model function. So it was prohibitive, but perturbation and differential allow you to solve it in a computationally efficient way. So I'm going to move on to spatial frequency domain. Anybody working on spatial frequency domain here? Yay! Bernard too. All right. And before I describe, okay, let me describe. So what happens is that the surface of the tissue is illuminated with these spatially modulated patterns. I think David showed some pictures, and in his pictures he's modulating so along the x-axis. So you're kind of looking down, and there's actually sinusoids, but you kind of see these bands of light as you're looking down. And so what happens is you illuminate. I think he actually uses, like, at one point he used just a standard projector with a slide to illuminate, and then you capture with the camera what comes out, and how that sinusoidal wave degraded in amplitude, as well as how it's shifted in phase, gives you information about the constituents of the tissue that cause that change. So before I describe this method, I think just briefly, before this method that I'm about to describe was derived, the way people would get spatial frequency domain results is that they get spatially resolved results, and then they would discrete Fourier transform them, and then use that as the spatial frequency domain results. However, there's a discrete Fourier transform in there, and that would cause discretization errors, possibly aliasing errors. So that motivated groups to find a way to circumvent that. And the way that we do that is we take the RTE. I have my little road map in a dash way. But the key thing that we do before we go into the roadmap is that we Fourier transform this along the I'll show you, along the X and Y axis, and then we get a Fourier transformed gradients. We do the method of characteristics to get a Fourier collision density, and then an estimate. So we start with the time-independent RTE. We do the Fourier transform over, that's the word I was missing, transverse dimensions over X and Y. I'm showing this, we always define these in the most general terms, but I have to say, honestly, I don't think I've ever seen an SFDI measurement taken where the sinusoids are also along the y-axis. But just to keep in full generality, this equation was performed over both X and Y axes. And what you end up with is an RTE that looks something like this. And I kind of highlight in red what the effect of the Fourier transform is. I put hats on everything because we're in Fourier space now, and this is what that looks like here. This method was devised and documented by Adam Gardner. So once we have that Fourier transform radiative transport equation, we use the method of characteristics. Integrating factor comes in. You don't know if that rings a bell, but integrating factors are our friends and allows us to simplify it to an ODE. We end up getting an integral equation that looks like this, where now this integral operator has a form with this new kind of highlight. There's other differences, and now it's only a function of z here too. And S, the term here has this new red term here too. So if we were to estimate reflectance, we would use this estimator that we had before. What we would do before I get to the estimator, because then I can define what these terms say, we would start a source, a point source, perpendicular straight in to the tissue. And that location would be at 0, 0, 0. So this x sub 0 is 0. And when the photon comes out the surface, the distance between that x0 and where it exited gets applied to this weight factor. Here's your spatial frequency, fx. We've got a minus 2 pi I here, and each collision is contributing to that, so that at the end, you would get something that looks like e to the minus 2 pi I, spatial frequency, x direction, x distance from where the point source is reaching. And I want to say a few words because I've had questions before about this. Like this is a complex tally. How do we do that in practice? We actually tally the reals together and we average them. We tally all the imaginaries together and we create an average tally. And then we determine the amplitude and phase of the resulting reflectance tally using those averages. Any questions about that? How about anyone doing temporal frequency? There's some doing temporal. Okay, well, in this case, an amplitude modulated source is injected into the tissue. And then again, what gets measured out, typically at a fiber or source detector separation, we look at the amplitude degradation and the phase change. And I'll just show ideas here. So like Gardner, or like the previous method, we start with the radius transport, Fourier transform with respect to time. Okay, we're taking the integral differential equation time dependent form. Okay, and then we do our thing. We change it, method of characteristics, we get an estimator, and then we get the appropriate way to tally temporal frequency. So here's time dependent Fourier transform with respect to time. This is the temporal omega temporal frequency. I get these red terms in here. This is the velocity of light. And Testor came up with this method. Oops. So again, we have this collision density in Fourier space. We have these components of K and S with these different terms. And I don't show you all the cancellations and what happens, but at the end, you would tally e to the minus 2 pi temporal frequency times time. Now, how do you find time of photon in a Monte Carlo simulation? What you do is you figure out the path length from source to detector, and you divide it by the speed of light divided by n refractive index of the medium, and that gives you the time the photon took from source to detector. So we use that again. We take the real and imaginary parts of this for each photon, run n photons, figure out which come out the detector, and then form the expected value. Okay. Do you have a question? Okay, good.
Actually, about the spatial frequency thing.
Okay.
Trying to wrap my head around what phase means in that case. You said you get the average of the real and the average of the imaginary,
yeah,
at a point away from the source, away from wherever the point is, and then
yeah.
What is, how I know what it means, like I think mathematically, but I can't figure out what it means
When I think phase, I think like the spatial phase of like you move the sinusoid
right?
spatially. So
Uh-huh.
what does it mean? This,
Well, because it is moving, see, the tally includes the distance the photon emerged relative to where it started.
okay.
So it's been shifted laterally. And what we would do, typically, although I don't think necessarily people use it in practice, we would take that real and imaginary form, arctan of it, and just like we would calculate phase and determine phase from the constituents, the real and imaginary estimators that we evaluate.
Remember that I can add something. I think if you have normal incidence of your illumination source, the reflected modulated light will not undergo illumination. However, if you have a weak illumination, the light, the modulated light that comes out will actually be spatially shifted relative to the illumination, and that's what this captures.
Okay.
And I think Andrea Bassi leveraged this ratio to actually gain a sense of calculating because it's an alter media depending on the thickness of the layer. And the contrast, it will change the shift, and the shift can be used potentially to look at out. So this happens with monochrome. But the rest,
I think so. When you think about phase, and we think about it on an electrical perspective, right? You have like RC circuit, you have something that get phase. But I guess when it comes to the current regime that we're talking about, the changes in the image diffraction or the changes in the speed on property.
right, I mean, this is a spatial measurement, so we're proposing a spatially modulated excitation when we're looking at the spatially modulated emission, and that spatially modulated emission will have a phase shift associated with it. We will also get lectures later on that where you actually can look at temporal excitation of the light, which is in the phase of the temporal emission. So you can do, you can do spatial or.
Maybe you would just want to run a simulation. I don't care how it's evolved. I just want to run it. So we have a library in which I call it conventional Monte Carlo code exists. We have 3 ways to access that code, and you'll see it different forms this afternoon. We have a command line. This has the fullest capabilities. We have the most sources. Jonica wrote the source code and took into account probably every physical conceivable source that you could want, external and internal to the tissue. Tissue definitions that are layered or have inclusions, and different detector definitions. We also have PMC. We have a MATLAB interoperability, which allows, like, maybe you're working in MATLAB, you're used to working in MATLAB, and maybe you want to run a simulation from there. We have that capability, and then we have a panel. Maybe you don't want to type at all, you just want to point and click. We have a panel that you can run Monte Carlo. Oh yeah,
It's open source.
open source, GitHub. Yeah. Lisa, this afternoon, will show you all the sites you can get our code. So this is actually our GitHub site. This is our GitHub site. And if you go to our homepage, go to the developers, you can get here, and then we can get to the downloads. We include sample in files in the downloads, so that a way to generate sample in files so that you can, this particular in file have every single detector that we have, I think. And on this right-hand side over here, we have all sorts of information about how to run files, how to edit files. They're all written in JSON, and the files are in JSON. And the source documentation that Jonica wrote is over there. So you can take a look on the right-hand side. But just to give you an idea, so this is kind of what the JSON looks like. And you give it output name where you want the results to go to, how many photons you want to run, how you want to seed your random number. I usually do reproducible because, oh, thanks, I'm debugging. Yeah, I'm not sure, it's working.
That's right.
So, I seed with 0 only because typically I'm debugging, and when I debug, if you run, it means that the random walks are run in the same order every time you start it up again, and that's helpful sometimes. But then you can make it totally random. We use something called the Mersenne Twister as our random number generator. This has got an enormous period, such that we do not, one of the things that you want to be careful on is that you don't start the random number sequence over again in case, oh, thanks, did you fix it?
I think so.
Oh, thanks.
Private engineer.
We use a phase function type. We typically use Henry-Greenstein, but it's surprising how often I use bidirectional one. So the bidirectional slab problem is one of the few versions of the RTE that's analytically solvable. And so sometimes it comes in handy to run things because you have an analytic solution for reflectance, transmittance, internal fluence. So it sounds kind of funny, and you'll see also in the integrating lecture, I think you might deal with a bidirectional RTE solution. We have a way to generate the databases. We have a diffuse reflectance and or diffuse transmittance. This is different than the PMC. Say you just want to, you don't really know where you want to put your detectors yet. So let's just run a database, save everything coming out the top, and then I can post-process that database with moving my detector sizes and locations around and play around with it without running another simulation. And you can also do provision, reflectance and transmittance. You can turn on Russian roulette, and this defines the threshold. And we have ways to do parameter sweeps. So David Kucha used our code to create his table lookup for the SFDI. And basically he wanted to create a table lookup of spatially reflected reflectance versus spatial frequency. And so he actually coded up this sweep. So you can, in the command line, say, I want to run it for this tissue optical properties, but then change VUA by this, and give it 10 values, right? And give US 10 values, and then it'll run, if you're in a parallel processor, it'll run in parallel and generate this results so that you can put them into a table lookup. Also, if you don't do a sweep, we have parallel processing. So we have all our, this is JSON, this is a very simple point source that we use for the SFDI and temporal frequency. You give it a point location, a direction, these are direction cosines, and do you want to start it in air or in the tissue? And this is where you find Jonica's nice documentation about all the different sources that he's coded. And then we define tissue. We put air up here, but you can change the optical properties as default, air below and above, and then the tissue in here, and then the optical properties and how thick this is. You can make it multi-layer. You can change the refractive index of the layers. You can include an ellipsoid. Ellipsoid was more derived from like tumorous, regions, but the need for voxel and cylinder came up because people were taking measurements on phantoms that they had made, and they had certain geometric shapes that they wanted to take measurements on, so those got derived. You can spell out your spatial frequency, and the only thing that I want to point out is that the tally is performed right at these special frequencies. There's no binning involved. So when that photon comes out, you say, how far is it from where it went in X direction? Okay, hit the weight is equal to minus 2 pi I spatial frequency, that distance. So you hit it right there, no binning. Whereas spatial for RO, source detector separation, we have to define the bins of the photons and gather it. So we define these RO bins. Collect the photons. Yes.
So the frequency they're using is it only in spatial frequency, or can you use that frequency if you're working
Right, frequency domain.
years?
Years, yeah, yeah, I mean, I'm not sure how you would model mirrors using our software.
I'm sorry, I missed the question actually.
So she mentioned spatial frequency. I'm thinking like frequency of years and modeling.
Yeah, I mean, you do, I mean, we do.
Oh, I'm thinking of, I was thinking.
Temporal frequency domain.
Yeah, I was thinking he was talking, yeah, right, we do just like this. We would define our special frequency. If you want help, anyone want help setting up a simulation, let me know and I'll work with you this week.
Right.
You would. Do you want to join our group and write code? What's that? Okay. Okay. And so in order to, our code, our Monte Carlo command line works Windows, Linux, OS 10. You give the command like this. Sometimes there's parameter sweep arguments you can give to spell out the parameter sweep like I described. And then at the end, after the simulation runs, we have these scripts that you can run. You just have to, the output file that you designated, just put that output file in a location in this file, and we have ways to plot all the results. And here are the units that we use. I mention this because our time is in nanoseconds, everything else is in millimeters, gigahertz, and wavelength is in nanometers. I say time because some time results were confusing to a user because he thought they were in picoseconds. And anyways, it's good to know the units that you're using in the software. So I want to just touch base on something called scaled Monte Carlo. It's used in the GUI, the forward and inverse panels use the scale Monte Carlo. I show it as a Venn diagram. It's separate from the conventional Monte Carlo because it's a different piece. What happens is Keeley and Patterson took the results of reflectance versus source detector separation and time, and then they provided a way to scale those results. So these I have run all the photons, they've averaged the photons already, and then what happens is, so you have this domain of space and time, and they show you how, if you change your optical properties, you kind of shrink and expand this map so that if you change them, you kind of know, okay, with these optical properties, my source detector separation that I'm interested in is here instead of here. So it's kind of a way of scaling the world and picking out the right one in the movement. It does not, oh, I should add that Michele Martinelli took this and found that he coded up their method, and he found that for large times and large detectors far from the source, the tallies in that were small. So he made these adaptive bins where he made the bins larger in large T and large rho. And then he added a non-uniform rational spline on top of the nerves to smooth out the data. So you'll see that. You'll see both in the GUI. And I tend to When I go to the notes. But bear in mind, these were not derived on a photon by photon basis, so they're different beasts. But they provide nice real-time results for homogeneous tissue, and you'll see that.
And the accuracy of that methodology is given that.
So,
There's
Oh.
just-
Photon type photon.
yeah,
You mean like how it's like, are you saying that they sort of changed the fundamental equations they're looking at, or are they like looking at it from a different perspective?
yeah, no, so the difference is they ran the Monte Carlo exactly like I described. They ran it exactly. They didn't change the random walk process at all. What they did is they only captured detector information. So they got reflectance versus source detector separation and time. They got the evaluation of that detector function at the top, and then they scaled that result. Yeah. So you can imagine, like, if you increase scattering, so say you lived in a world and scattering was something, and here's the detector that you should pick off, then you say, oh, well, I want to know the results by increased scattering. It would actually bring in this detector. So things like that. They figured out how to reweight the result. That's why they didn't reweight each photon on the photon. So hopefully we've gained exposure, a little bit of understanding potentially perturbation differential, Monte Carlo, how the estimators for the spatial frequency and temporal frequency domain are derived, and then how to run a Monte Carlo.
And we'll do some of that this afternoon.
We will. We will.
Thank you.